Some learning objectives for this week. Sorry if the face box is in the way a little bit there, but I'll get that adjusted for us. We want to understand the key geographic concepts related to atmospheric humidity and adiabatic processes. I know adiabatic might stand out as a big word for us now, but we'll dive into that later and get to understand it and see how it relates back to some of the other processes that you've been studying about in physical geography. Yeah, second, we want to utilize the sling psychrometer readings to compute relative humidity and dew point values. Okay, and then thirdly, we also want to calculate relative humidity and temperature values using appropriate variables, formulas, and rates. So those are our objectives to keep in mind, and we'll see how those play out throughout this little mini lecture and in the actual lab itself. So humidity, we can think of as the quantity of water vapor within the atmosphere, recalling that water vapor is a variable component of the atmosphere, right? By no means is it the same in terms of precise values, right? It's not going to be the same anywhere on Earth at one time, or at least there's immense variation, we could at least say. And as geographers, we take a keen eye to the patterns of those variations and amounts because of all the information that it tells us about what's going on. And also keep in mind that amounts of water vapor vary place to place and over time. So it's a little bit fleshing out a little bit more so what I was just referring to, but adding in the time factor, how through time these aren't stagnant values in any one place, and in any set amount of time we can see patterns as well, similar to how we look at patterns across space. So charting weather throughout the year is a great example, right? How much humidity plays into our weather. So a little bit of contextualization for how varying across place and time there. And also let's keep in mind, remember learning how temperature is the most important determinant of the amount of water vapor that a certain volume of air can accommodate. It might, at first listen or first glance seem a little different to think of a volume of air, but oftentimes we think of volumes of water, but air, we apply the same principles. There certainly are volumes of air. If we look at our inner tubes of our bicycles, for instance, it's a neat visualization of a very specific volume of air, and in weather and studying the atmosphere, these are key principles to keep in mind as well. So humidity and temperature, the warmer the air, the greater the quantity of water vapor the air can uptake. Air over the poles can be less than 0.2% by volume of water vapor, and air over the tropics can achieve up to 5% by volume. And we see that in this satellite image here, being represented by, I'm just going to try to move the face box for you there a little bit, but right down here around 10 degrees north, see some very higher amounts anyway of, indeed we could say high amounts of water vapor compared to, certainly compared to 20 to 30 degrees north latitude, but a little bit over here is a little bit of orange, and on our scale here, orange is a little bit less water vapor than the purplish amounts, but anyway, it illustrates how in over the tropics, or in this case, getting closer to the tropics. The trade winds here. Yeah, there's higher moisture there compared to, in those clouds, higher amounts of water vapor being held compared to just the white and blues of our low pressure cell here sitting off the coast of British Columbia and Alaska. So capacity, there are limits to the amount of water vapor a volume of air can accommodate. As air achieves the maximum uptake of water vapor for a volume at a given temperature, remember, the air becomes saturated. So keep in mind that the temperature at which saturation occurs is the dew point temperature, and we're working towards that here. So if dew point temperature stands out as new to you, or at least in lab, we probably learned about it in lecture, but if that's new, we can rest assured we're going to work towards it in a little bit here. But there's a further uptake of water vapor or cooling will result in active condensation. Okay, this is the phase change of vapor to water. And as the temperature of a volume of air increases, the water vapor capacity also increases. So let's take a look at that in terms of a neat chart here. We have on the y-axis grams of water vapor per kilogram of air. And below we have, on the x, we have temperature. And we see that with a lower temperature, we can have, it's holding a smaller amount of grams of water vapor per kilogram of air. And vice versa, as you get up to 80 degrees Fahrenheit or about 27 degrees Celsius, sample B is holding a lot higher amount, more than twice the amount of water vapor. And that's illustrated, that more than double, right? That exponential rise is illustrated in our J curve there. So dew point temperature, the temperature at which air becomes saturated. As air cools, the relative humidity increases, right? And dew point temperature occurs when the actual amount of water vapor and the maximum amount of water vapor for a given volume are the same. Okay, so and that's when you have relative humidity equaling 100%. Relative humidity, you've heard me bring this word up, this concept up a couple times now. So it can be defined as the amount of water vapor in a volume of air. And it's commonly expressed as relative humidity. Relative humidity is a measurement of the actual amount of water vapor compared to the maximum amount of water vapor at a given temperature. So it's this content over capacity. And then we multiply that by 100 to get us a nice percent value. And the mixing ratio, I know we're introducing quite a few terms here, but this will help us for understand the foundation for our lab work. So yeah, one more slide and then we'll get into a little bit different concept for you. So expression of relative humidity. Okay, it's the ratio of grams of water vapor per kilogram of dry air. And the vapor and air mixed, although we think of some ratios, you might be able to visualize that 10th grade glass beaker of nicely divided substances, maybe an oil and water ratio, or just to give you a little bit of a visualization there. But the water vapor and dry air, they're completely mixed. So yeah, it's just something to keep in mind, because so often ratios can be visualized as two distinct substances. So the saturation mixing ratio then is the maximum number of grams of water vapor per kilogram of air at a given temperature. And the actual mixing ratio is the current or actual number of grams of water vapor per kilogram of air. And again, a lot of words there, but we see that it's quite easier to comprehend when we see it written out. Relative humidity equal to the actual mixing ratio divided by or over the saturation mixing ratio times 100. Again, this content over capacity. And that other concept that I was referring to, or device, we can really conceive of it as is the sling psychrometer is what helps us in calculating these relative humidities. Okay, in measuring it rather. Consists of two thermometers, and one's the wet bulb and one's the dry bulb thermometer, and on the end of the wet bulb is a wet cloth. I have a larger image of it here for you in a second, but the lower the relative humidity, the more rapid the evaporation and the greater the difference between the wet bulb and the dry bulb temperatures. Okay, that's our other key point to keep in mind for this slide. But to get back to looking at the device itself, I have a little video coming up for you in a little bit, but it's yeah, really straightforward technology with the handle and with a central pivot and the two different thermometers. You spin them around for about a minute, and generating evaporation of the wet cloth sock, and then you take the two different values of the thermometers after that. Okay, so it's the slides are acting up here for a little bit for you. So it's the difference between the dry bulb and the wet bulb is referred to as the wet bulb depression. And the psychrometric tables, which are part of our lab, and they're included as files as well, tables with a bunch of different values on them. These are used to find the corresponding relative humidity given the dry bulb temperature and the wet bulb depression. The psychrometric tables are also used to determine dew point temperature given the dry bulb temperature and the wet bulb depression. So there'll be two tables for you to get to look at. And as we say here, both tables are included in the Lab 7 page. So the procedure is to dampen the wick or the sock of the wet bulb and gently spin the psychrometer for at least 60 seconds. Just a side note there, a bit of an interesting word, psychrometer. It's psychro stems from Greek meaning cold. So it's a bit of a etymological insight there for you in terms of how we're able to, where this comes from. Okay, and so we record the dry bulb temperature and then record the wet bulb temperature. And we subtract the wet bulb temp from the dry bulb temp. This difference is known as the wet bulb depression. Once you have the dry bulb temp and the wet bulb depression, you get to determine the relative humidity using the appropriate relative humidity table. So it's a pretty straightforward one, two, three progression there. And let's see if our text serves us well here in coming up with this.
A sling psychrometer is made of two separate thermometers. One that is known as the wet bulb. The wet bulb will have the stars on the bottom of the thermometer, and the other side is known as the dry bulb.
Let's see if that's working out there.
What we do is we need to get wet. So this gauze section right here, we take and we dip into some water. So we bring some water over here. You don't have to get it too wet. Just want to dip it in there. So it's a little bit wet. And then what you do is spin it around, not too fast, not too slow, for about 30 seconds or so. Notice how I'm not spinning it too fast, but I'm not spinning it too slow. The reason we have to spin it is because the wet bulb temperature tells us the temperature that water is evaporating. So we need to spin this around so that the water does evaporate. Okay, so then we take our reading. So this is my wet bulb. I want to get my temperature. If I read here, this is in Celsius. So this would be about, looks like it's above the 12 there, but it's about 12 degrees Celsius. So I'm going to record this on my board. So our wet bulb temperature is 12 degrees Celsius. And my dry bulb temperature, the thermometer that doesn't have the wet gauze on it, is in between 16 and 18 there, so we'll go with 17 degrees Celsius. Okay, so this sling psychrometer gave us the wet bulb temperature and the dry bulb temperature. In order to use it to find relative humidity and dew point, we have to use these temperatures and consult our reference table. So first, let's look at our relative humidity. Our relative humidity, we need to know our dry bulb temperature.
Okay. That's okay, so that's a neat little video, little visualization for how that the sling psychrometer works. And we have our example here with a little bit different values than the video. But let's say the dry bulb measured 19 degrees and the wet bulb 15 degrees. The difference is 4 degrees. So let's find the relative humidity using the relative humidity table. And so we have the difference at 4 degrees and our dry bulb temp here. Two different lines helping us out there. So right in between, our 19 was just in between 18 and 20, between 64 and 66 there. So we have our dry bulb temperature versus the wet bulb depression, the relative humidity equal to 65%, pretty high. Okay, and the reminder here is to be as accurate as possible. If the dry bulb temp is an odd number, or if the wet bulb depression is not a whole number, you must calculate the average between the given numbers on the table. Okay, and the splitting of the difference, so to speak. The average x plus y divided by 2. Okay, so now let's look at the dew point temperature, very similar process in terms of using the charts. The temperature at which saturation occurs. And a bit of context there, as air cools, the saturation specific humidity, or maximum humidity, increases. Okay, and so in continued cooling, with continued cooling, air will become saturated. Saturation specific humidity and specific humidity reach the same temperature. And it's important to keep in mind that the air contains the maximum amount of water vapor that it can accommodate. Continued cooling results in forced condensation, such as what happens in refrigerators. Right? The dew point temperature, continued here. To determine the dew point temperature, we apply the dry bulb temp and the wet bulb depression values to the dew point temp table. So it's a different table. It's the second one that you'll have. Okay, so the same values here as the first time, and we want to indicate the dew point temperature using the table. So wet bulb depression of 4 again, and our dry bulb temperature was 19 degrees. So 11 and 14. But we want to be at 19, so split the difference there, so 12 and a half. And yep, I said it a little bit too early there for you, but again, being accurate as possible, right? averaged out the 11 and the 14, divide by 2, or you can, whichever other little shortcut that you have there for getting the accurate value. Next we want to look at the mixing ratio. Okay, so the relative humidity can also be determined using a graph rather than the tables. Okay, and expressed as the mass or the weight of water vapor in a given mass of dry air. Grams of water vapor per kilogram dry air. So here you have the saturation mixing ratio of water vapor, grams of water vapor per kilograms of dry air, and temperature along the x-axis. This is the mixing ratio. Got into a little bit earlier. It's the mixing rate. The relative humidity is the mixing ratio divided by saturation mixing ratio times 100, right, to get it expressed as a percentage. So, for example here, to calculate the relative humidity, if the air inside this room has a temperature of 21 degrees Celsius and a mixing ratio of, 5.8 grams per kilogram. 21 degrees Celsius is a little handy one because that's right about 70 degrees Fahrenheit. So we're all pretty familiar with a room temp around 21 degrees Celsius if you're not super familiar with Celsius values. Okay, so let's use the saturation mixing ratio graph to determine the saturation mixing ratio for a given temperature. Right, in this case, 21 degrees. So we have our graph, and we've plotted the values here. We have 21 degrees and about 16 grams of water vapor per kilogram dry air. Okay, so we have a simple division then that sets us up with 5.8 over 16. We're going to multiply that by 100, and this equals 36.25%, right? 36.25% relative humidity. So it's a neat way of seeing how we can combine the different variables at different points in the equation to come up with a different variable. And this is part of what you'll be doing in the lab, being given one of these values, or two of the values, and having to come up with the third one. It's similar to what we just did right here. Okay, and then this final part of the lab, I want to continue working with some of these principles and understand adiabatic processes a little bit better. And just to jump to my fourth bullet point here, I don't know if that's showing it for you, the full description there, but adiabatic, this word, it's not too commonly used in common parlance, but it comes from Greek in terms of etymology, and for not, right? A lot of our words that start with a indicate a negation of something, and then diabatos, or however it's pronounced in Greek, right? But to be crossed or passable. And so, we can think of not passed, or not going through. And really this is a really neat conception of how a parcel of air warms and cools as it rises or falls. that there's, adiabatic is used in thermodynamics and physics. That is, it's a very key concept in terms of not losing heat, no transference of heat, and in this case it's because there's no transference out of a set system. It's just that it's being enlarged or compressed as with changes of air pressure as it rises or falls. So this leads us to say, as a parcel of air ascends, right, the pressure decreases with altitude. We looked at that quite a bit last week, and the air cools by expansion. This is adiabatic cooling. As a parcel of air descends, the pressure increases, and the air becomes warmer as it's compressed with higher pressure, right? And this is adiabatic warming. The amount of vapor within a parcel of ascending air will determine its lapse rate, which is the rate of temperature decline as the altitude increases. So, if an ascending parcel of air is unsaturated, that is, the relative humidity is less than 100%, it will cool at a dry adiabatic lapse rate, which is 5.5 degrees Fahrenheit per 1,000 feet, or in Celsius, very handily, 10 degrees Celsius per 1,000 meters. And Celsius coming in really handy with its divisions of 10, multiples of 10. And a descending parcel of air will warm. As it descends, it compresses, right? We can visualize a mass of air rising up the Sierra Nevada and then descending the other side, descending and compressing at the dry adiabatic lapse rate. And we'll look at why a descending parcel of air will warm at the dry adiabatic lapse rate in a little bit, but maybe that's a question I'll pose for you all. Why will a descending parcel of air, why would it be warming at the dry adiabatic rate? Okay, feel free to pause the video and think that through for a little bit, add it to the discussion board. Nevertheless, we see the value here. It's the same as an ascending parcel, a rising parcel of air at the unsaturated rate. And then let's keep in mind here that if a parcel continues to rise, this is right as it's rising on the windward slope, as it may encounter the temperature at which it cools to a dew point temperature. It becomes saturated. This is at the lifting condensation level is what this is known as. So the altitude at which clouds form due to active condensation. And just to flesh out saturated air, it's the air that is holding all the water vapor molecules it possibly can at a given temperature. So ascending saturated air will cool at a different rate, right? Because it's full of water molecules. Think of it as water vapor. This is water vapor begins to condense. Right? Ascending saturated air will cool at the saturated adiabatic lapse rate, which is 2.5 degrees Fahrenheit per 1,000 feet, or 5 degrees Celsius per 1,000 meters. And this is as you can tell, this is a lower rate than the dry adiabatic lapse rate. And it cools at that lower rate because of the release of latent heat as the vapor condenses. And I'm sure you flesh that out in your physical geography lecture, but just a little reminder there of the release of latent heat as vapor condenses. So let's take a look at a little example. And we have ascending air cools at a dry adiabatic lapse rate of 5.5 degrees per 1,000 feet. and ascending air reaching a lifting condensation level at 3,000 feet becomes saturated. And this is our hypothetical example here of 3,000 feet. These mountains in the diagram are only in a lot of places of the world. 4,000 feet is quite a large mountain. In fact, if you're starting from sea level or down at 1,000 feet, it's a lot to climb up 4,000 feet, right? So I shouldn't say only, but compared to the Sierra or many other, Sierra Nevada of California or many other mountains in the world, 4,000 feet is not a lot. So that's where my slip in saying only came from. But let's imagine we're in, let's say, northern New York State in the Adirondack Range, right? A classic range of 46 peaks being over 4,000 feet, or at least that's what they were originally estimated to be, measured to be, and so that's a tangent for you. But we're somewhere in the Adirondacks, and the lifting condensation level, right, is level at which becomes saturated is 3,000 feet. So let's work through some of these formulas based on this little schematic. We have ascending saturated air cools at a saturated or moist adiabatic lapse rate of 2.5 degrees Fahrenheit per 1,000 feet. And then the air crests the mountain, okay, reaches the leeward slope, right? We work up the windward and reaches the leeward side and descends at the dry adiabatic lapse rate. So if the temperature is 70 degrees at 1,000 feet, down where you're starting, on the windward side, what is the temperature at 1,000 feet on the leeward side over in the rain shadow? Okay, so let's think about calculating the temperatures for every 1,000 feet on this mountain profile diagram on the windward and leeward side. We're given these two different lapse rates, dry and the saturated. What you need to think about is as it ascends the first 2,000 feet, we're going to be at the dry adiabatic lapse rate. And it cools enough, right? We learned about last week different rates for atmospheric cooling as you rise in altitude. It's going to cool. We're going to reach the condensation level at 3,000 feet, as we've given, and then air saturates, and then the final 1,000 feet we need to calculate at a different rate, so at 2.5 degrees Fahrenheit. Then once you reach the other side, it's going to be 5.5, 5.5, 5.5. So how this plays out is, right, go starting at 70 degrees, go up 1,000 feet, lose 5.5 degrees, go up another 1,000 feet, lose 5.5 degrees. It puts us at 59. But then, right, we've reached saturation, so we use the saturation adiabatic lapse rate, 2.5 degrees per 1,000 feet. And it's that same temperature on the dry side at 4,000 feet. So then we subtract 2.5, 2.5, reaching back down to 1,000 feet on the leeward side. And we're at 73 degrees Fahrenheit. So that's an example of how you can graph this out on the visualize it on the chart that on the graphics that are given in the lab. And introduction to some of these key concepts that we see this week related to humidity and adiabatic processes. And so with that, I'll turn it over to you all for questions in the discussion board. And as they come up, we can work through any of the questions that you have in the lab together, but that'll do for now. And thanks for listening, and I look forward to our discussions. I look forward to your questions and discussing these with you. Okay, take care.